Hello student, I am Kavita Katole and we are going to study the architecture block diagram of 8085 microprocessor. Now this is the functional block diagram of 8085 microprocessor. You can see the different blocks in the architecture or in the functional block diagram. So we will go for the detailed description of each block one by one. So first of all the signals in the 8085 microprocessor can be classified into six groups. That six groups are: first is address bus, second is data bus, third is control and status signal, fourth is power supply and frequency signal, fifth is interrupt and peripheral initiated signals, and sixth is serial IO ports. So we will go one by one. The first one is the address bus. So we can see at the right corner there is address bus, name given as A15 to A8. Actually the 8085 is having the address of 16 bit. This 16 bit address is stored in two part: 8 bit as A0 to A7 and next 8 bit as A8 to A15. So we can see this address buffer of 8 bit and one more data address buffer which is carrying the first 8 bit of address. Now the data bus, that is data slash address buffer of size 8, having two-way arrow which is indicating that it is bidirectional bus. Bidirectional means the data can transfer from memory to processor or from processor to memory. Now, the AD0 to AD7 is called the multiplexed bus. Multiplex because it can carry the data as well as address. So, it is carrying the 8 bit data and the first 8 bit of the address. The next is control and status signal. So for that we will go to the timing and control unit which is showing the different control signals. So I am first starting with the address latch enable ALE pin. We can see the ALE pin on the timing and control unit. Now what is the role of this ALE pin? It is used while multiplexing the address and data at the address data buffer. Means at a time either the line will use for A0 to A7 address or D0 to D7 data. So it is given by the address latch enable pin, which will enable the multiplexing to transfer the address. Next is RD bar and WR bar signal. RD is a read signal which is active low, and this signal indicates that the selected input output or memory device is to be ready and data are available on the data bus. So whenever the read signal is active low, it means the IO device or memory device is ready to read. Next is WR, that is write signal. This is a write control signal. Again it is active low. Active low means pin is activated. This pin WRB WR is activated when the input bit 0 is given. Active low means bit 0 has to give the signal, and active high means bit 1 should be provided. So again, right bar is a active low pin. This signal indicates that the data on the data bus are to be written into a selected memory or IO location. So whenever the write operation has to perform, the WR pin is made active. Next pin is IOM bar. IOM bar is a status signal to differentiate between IO device and memory device. So whenever the pin is high means it indicates an IO operation, that is input output device operation, and whenever the pin is low it indicates the memory operation. Now we will go for the next pin at the timing and control unit, and the pin is S1 S0. This pair of the pin will give the status of the signal again for IO device and memory device. Since these pins are working together, S0 and S1 status for 00, 01, 10 and 11. So there will be a 4 status for IO device and memory. Next we are having the clock signal, that is clock in, clock generation, clock out X1, X2, which we called a power supply and a clock frequency signal. Here at the 8085 processor, we have to give the plus 5 volt power supply, which is VCC, and VSS is a ground reference. The X1, X2 are the crystal connected at the pins. The frequency is internally divided by 2. Therefore, to operate a system at 3 megahertz, the crystal should have frequency of 6 megahertz. The clock out pin is used by the system as a clock signal. The fifth type of signal at the processor is serial input output signal, which we can see at the upper side on the 8-bit internal data bus. This is a serial input output control. Here actually we are transferring the data bit by bit, that is called a serial transmission, and the two pins are there, that is serial input data, that is SID, the arrow is inward, and SOD, that is serial output data. So whenever the data is uh, out from the processor, we are going to use the SOD, and whenever the data is in from the IO device to the processor, we are going to use the SID, that is serial input data pin. The sixth type of signal we are going to see over here is interrupt and externally initiated operations. So interrupts pin, mainly we are having the 5 interrupts, that is INTR, RSTs and trap. Now INTR is the interrupt request pin that can be used to interrupt a program execution, and the microprocessor acknowledgement by the pin INTA bar, that is interrupt acknowledgement. We can see the INTA bar, that is interrupt acknowledgement. The next interrupt pins are reset pin, which is divided priority wise in three parts: RST 5.5, RST 6.5, and RST 7.5. These are the RST interrupt. And trap is the fifth type of interrupt. Again, the externally initiated operations are done by the pins at the control unit, that is reset in and reset out, which is at the timing and control unit. And to respond a hold request, we are going to use the hold pin, and for the acknowledgement it is HLDA, that is hold acknowledgement. So this is about the signal. Now we are going to see the register part of the 8085 processor. So first of all, we can see at the right side there is a register block, a big one, having the register WZ, BC, DE and HL. So 8085 actually containing the 6 general purpose registers, and these 6 general purpose register are B, C, D, E, H and L. All these are of size 8, that is it can contain maximum 8 bit. W and Z are the temporary register which cannot be used by the user, it can be used by the processor only. And next is the uh, if we have to uh, use the 16-bit data, in that case we can use this general purpose register in a pair like BC, DE, HL. At the above part of this register there is a multiplexer. Multiplexer is used to multiplex or demultiplex by the processor to select one of the register from this stack of the register. Then there is a stack pointer of 16 bit. Stack pointer is a memory pointer to save the stack memory address. So stack memory address is a 16-bit address. That's why the size of the stack pointer is a 16-bit. Below that there is a program counter, again a 16-bit register. This is a special purpose register. This is not a general purpose register. Program counter containing the 16-bit address while the execution of the program, means it is having the sequence of the next code or next instruction in the program counter. Then there is a 16-bit increment decrement address latch. When we are multiplexing the address and data, the address latch is auto incremented or decremented by 1 by this part. At the left side, we can see the accumulator of the size 8. Accumulator is also called the register A, which is directly connected to the main part of the processor, that is arithmetic and logic unit. Since the arithmetic and logic unit of the processor is of size 8, we can say the 8085 is a 8-bit processor. It means it can process maximum 8 bit at a time. So accumulator register A generally used to store the result. Some implicit addresses can be uh, done at the accumulator. Now there is one more temporary register which is used by ALU, that is arithmetic and logic units. The next part, that is a flag, which is containing 5 flip-flops, is connected to ALU. What is the flag? Flag is nothing but a register. Again it is 8-bit register, but the 5 flip-flops are active, which is indicating the different status of the result or data. Whenever we are performing any operation, whatever the status of the result, that is stored automatically by the arithmetic and logic unit at the flag register. There are five flags, and these flags are sign flag, zero flag, carry flag, parity flag, and auxiliary carry flag. So whether the sign of the result is positive or negative will be indicated by sign flag. Whether the parity is even or odd will be indicated by parity flag. Whether the result is 0 or non-zero will be indicated by zero flag. Whether the carry is generated after 8-bit addition is indicated by carry flag. And auxiliary carry flag is used whenever a intermediate carry is generated after board 4-bit. So auxiliary carry flag is used by ALU only. No one can alter the data of AC, that is auxiliary carry flag. Remaining 4 flag can be used by the user. Now beside the ALU again there are two register, that is instruction register, and below that instruction decoder, that is machine cycle encoding block. Instruction register, again an 8-bit register containing the instruction that has to be processed by ALU. The instruction, for example, move, that is data transfer instruction, add, what are the opcode or machine code of the instruction that has to be performed on the priority basis will be first stored at the instruction register, and then it is moved toward the ALU via instruction decoder. Instruction decoder will decode that instruction, means what is the actual operation has to be taken out. So these are the different blocks of the 8085. The buses, we can see the data bus, the main 8085 internal data bus is of 8 bit, which is connected to a different block, and address bus is shown downward. So this is how the 8085 processor work together with address bus, data bus, and control bus, with ALU and with different control signals. Thank you.